Okay, we are continuing on here, chapter 17. And last time we were doing some calculations. We have our delta G naught is equal to minus NF E of our cell. So again, this is our one that we talked about last time that relates E of the cell to delta G. We also saw E of the cell is equal to RT NF natural log of K. So this is the one, again, that relates cell voltage to the equilibrium constant. And as we sort of talked about with all these, if you have E of the cell that's positive, that again should yield you a delta G that's negative, which means the reaction is spontaneous, and probably should yield you a large K value, as again, they all should sort of agree with each other. And opposite is true if you got an E of the cell that's negative. That negative, along with this negative, will turn our delta G into a positive, which means the reaction is non-spontaneous. And if you calculate K, we would expect it probably to be more on the small side. Now, we also talked about at the end there sort of non-standard conditions. And that is the Nernst equation. And that is E is equal to E naught minus RT NF natural log of Q. So remember that this is the equation that we use in some type of non-standard conditions. Typically, the two major things that would sort of push you into that equation would have to do with molarity. And again, 1 molar is sort of standard conditions, and also pressures as well. 1 atmosphere is standard conditions. So if you're dealing with something like we did, I think, in the last example, that maybe the concentrations are not all 1 molar, then you would be under this sort of standard condition. Obviously, the E here is our cathode minus our anode, as we've been talking about. F is Faraday's constant, R is our gas constant, which is the 8.314 version, and obviously Q in this case is our reaction quotient. Remember that if you remember the Nernst equation and you want this equation at equilibrium, that's basically how we get there. E is equal to 0 and Q would equal K. And if you substitute that and rearrange, you could get yourself back to that equation there. Any questions on any of that there? All right, so next thing we're going to talk about is batteries and a little bit about corrosion. You're not going to be responsible per se for any specific sort of reactions for batteries. It's more of a general how they're maybe similar and how they maybe vary from a traditional galvanic cell. So let's talk about a battery. A battery basically is a galvanic cell, or really a series of galvanic cells that are together, that can be used as a direct electrical current. It is self-contained. There's no sort of salt bridge. If you ever look right in the battery compartment of something, there's usually some wires, right? And it's the same idea. You got your oxidation reduction reaction happening. Those electrons go out through the wire through your device and power your device and come on back. Also, why typically need to put the batteries in the correct direction to make it a spontaneous process. If you put the batteries in sort of backwards, it will not work because you basically made a non-spontaneous process occur. Got to flip them around, obviously, to the correct sort of orientation. So the first type of cell we're going to look at is what's sometimes referred to as a dry cell. And in this particular case, I'm going to go with the Duracell. Looks like it. And the anode here is the zinc can or container that's in contact with MnO2 and an electrolyte. So in the middle here is sort of this paste, battery acid, if you will. That is sort of what's serving as like the salt bridge in this sort of situation. We have the cathode, which is the carbon rod that's inserted. Again, we have our electrons, right, heading sort of this way in the reaction towards our positive side here. This type of battery will give you basically a 1.5 volts. It doesn't matter the sort of size of it. There's different sizes, right? Triple A's, double A's, right? C's, D's. But they all will give pretty much the same voltage. The difference is obviously larger batteries have a capacity, obviously, to continue the process a little further. If we look at sort of the half reactions here, we do see zinc goes from 0 to +2, so it is getting oxidized in this particular case. Here over here, our Mn is -2 there, -4, +4. Over here, -2 is -6, and +3, going from +4 to +3 in this case, getting reduced. And we get the overall reaction that's happening here. And a lot of times when you do have some solids in the overall reaction, that's actually a fairly good thing. It allows sort of the battery to continue to function pretty well. Another type of battery is a mercury battery. It's used a lot in medicine and electronic devices and industry. And in this type of battery, we have the zinc again in contact with mercury as our anode. And again, we have the steel sort of container acting as our cathode in this particular case. This is in contact with a really strongly alkaline solution like KOH. Alkaline, right, means basic. So here again, sort of acting as the sort of salt bridge in this particular case. And again, if we kind of look at what's going on here, we got zinc going from 0 to +2. So once again, being oxidized. It is actually the mercury here that is going from +2 to 0 in this case, and it is getting reduced in this particular case. Once again, when we do look at the sort of overall reaction, we have a lot of solids and liquids, and as I mentioned a second ago, that's really good for sort of long life, if you will, of batteries. Also, in terms of rechargeability, that's actually a really good thing to sort of have that. You get a little bit smaller of a voltage with this type of battery, a 1.35 volts, but it is a little higher capacity and a little longer life because of sort of the overall products that are made and reactants in this case. Another type of battery is the classic lead storage battery, which is a lot of times your car battery. And that is 6 identical cells basically together. Each cell gives you about 2 volts. That gives you like 12 volts when you turn on your car, and that should be enough to kind of kick over all the electrical components and get the car kind of started, unless, of course, you're late, and then it will never turn over for you, right? And all that good stuff, and hopefully it's not dead. We have both an anode and a cathode that's immersed in a sulfuric acid solution. Again, a fairly strong electrolyte solution, sort of a salt bridge type of situation, sort of occurring in that case. It is rechargeable. That means the battery can reverse its normal electrochemical sort of processes. If you ever had to jump your battery, right, you leave it running for a while, right, to kind of charge it back up and all that good stuff. We also have like alternators usually in cars and stuff like that, so we don't kind of just drain the battery and stuff. You could check for a healthy battery by looking at its density. In a kind of colder environment, sometimes everything gets a little bit more viscous and it results in a little less power happening. Here is a cross section of a car battery, a traditional car battery. Again, we have our 2 terminals, right, where everybody wants to try to remember which one goes on which, right, which one should connect if you want to jump it. Again, you can see our series of cells in there. Also, sulfuric acid, you're usually pretty sealed these days. Can't really get in there to the electrolyte or battery part of it. Acid, again here, lead going from 0 to +2, getting oxidized. And on the back end here, actually, it is this lead that's going from +4 back to +2 and getting reduced. Once again, much like the other ones, a lot of solid and sort of liquids were made here. And again, that's really good for long life and rechargeability of batteries. A solid state lithium battery is another type of battery, and the anode is a conducting carbon type material like graphite that has holes in it that allows the lithium ions basically to travel across as they lose their electrons. It also, in the cathode, has a transition metal that could hold these kind of lithium ions that are going here. It's a really light metal, which is why a lot of times they use it for batteries and stuff, like your tools and stuff like that, right? You get lithium batteries and cell phones and stuff like that. It can be recharged hundreds of times without deterioration. And again, a lot of that sort of solid material that's made is going to help it with that. Another sort of type of battery, which is not a traditional battery, is a fuel cell. And a fuel cell is an electrochemical process that requires a constant supply of gas in this case. This is a hydrogen sort of fuel cell, so you need hydrogen gas and oxygen gas really being bubbled in here. And in this particular case, we see the hydrogen going from 0 to +1 getting oxidized. Here, the oxygen going from 0 to -2, becoming more negative in this case. And originally, a long time ago, this is sort of what they wanted to make cars run on because, again, the overall sort of reaction that you produce is water in this case. Obviously, we're not really a hydrogen sort of economy, and we moved away from that to more battery operated, straight battery and hybrid type of situation. All right, so in terms of batteries, like I said, you're not responsible for any specific reactions. You do need to maybe be able to contrast, again, a galvanic cell you would build in the lab versus sort of a battery, compare and contrast. Another thing here we're going to talk about is corrosion. And corrosion is really returning metals to their natural state. It is, for a lack of a better description, pretty much what happens when metals go through oxidation. So when a metal goes through oxidation, it's basically going through corrosion. A fifth of steel production is to replace rusted metals. Now, when we have metals that are sort of in contact with oxygen and have an SRP value, which is our standard reduction potential value, less positive than oxygen, what happens in that situation is if you have a metal with a less positive SRP than oxygen, when these two get together, what we know is the more positive SRP value will be your cathode. So in this case, the oxygen would be our cathode, and our anode in this situation would actually be the metal, which is going to cause the metal to basically spontaneously go through oxidation and corrosion basically here. So when metals that have a less positive SRP value than oxygen, it's very susceptible to going through corrosion because you're pretty much going to create a spontaneous galvanic cell where the metal will basically be your anode and go through that oxidation process. Now, not all oxidation of metals are necessarily a bad thing. What can happen sometimes is as the metal goes through oxidation, it will create a layer of oxidation that actually will sort of protect the metal underneath it from further oxidation. So aluminum's an example of that. Aluminum will make this sort of aluminum oxide, and the result of that is more metal that's underneath it will actually be protected from further oxidation and sort of corrosion that occurs. The problem, though, for example, is like what we have with rust. When iron does that and goes through oxidation, its little layer that it makes actually is pretty brittle and will just fall off. And the problem with that, obviously, is in the case of iron, when that rust sort of falls off, now you have brand new metal that's ready to go for some more oxidation and corrosion that can happen. Sometimes oxidation costs a lot of money, right? Copper that goes through oxidation makes that kind of patina color that people like a lot. Silver can tarnish, which is silver sulfide. And gold with an SRP value of 1.5 basically will not go through any corrosion in air or with oxygen. And that's because when we hook up gold and oxygen together in sort of a galvanic cell, with gold having a 1.5 SRP value, gold's actually more positive, which means the gold would actually be our cathode, and the anode and oxidation would occur over there at the oxygen. Thus, gold itself will not go through basically oxidation or corrosion because of that, and its sort of more positive SRP value. Now, as I mentioned before, rust is a little problematic because it does fall off, and the sort of oxidation of iron happens in a couple of steps. The first thing that happens is we do form iron 2, and then the iron 2 continues to sort of go through oxidation and eventually will oxidize itself out into iron 3 oxide, which is rust. And basically, for rust to occur, you basically just need three things: a little bit of iron, a little bit of oxygen, and a little bit of moisture. And iron typically has these sort of non-uniformal spots on it. And these are kind of like little valleys where it's very easy for moisture to kind of sit. And because of that, it will kind of start that process of rust to occur that can fall off. Obviously, here, going to cost a lot of money to fix that if things rust right through along the way. Now, there are a couple of ways that you can prevent corrosion. And let's talk a little bit about some of the ways that you could do that. One way is you could paint or do some type of metal plating, right? They sell Rust-Oleum paint, right, as a way to prevent your metal from rusting. If you paint it, it makes a nice layer on it. You could use chromium and tin, use the plate steel. They form this sort of very durable oxide layer. Galvanizing, which is zinc. Once again, when you do that, if you take iron and zinc and put some galvanizing on it, which is zinc, when we now compare the SRP value of iron and zinc, iron actually is more positive and will become more the cathode, and the zinc is a little bit more negative and would be our anode. So in this particular case, that's going to sort of cause the oxidation to occur on the zinc, thus protecting the iron that's obviously coated in the zinc. Zinc acts, as it says there, as sort of a sacrificial sort of coating where all the bad stuff happens to it, but basically the integrity of your iron or steel is still in one piece. You can also do some type of alloying where you can combine other elements together, which will change the SRP value, a lot of cases, to that of noble metals. Noble metals, like gold, are again pretty much chemically inert. They're not very reactive. And again, by doing so, you can kind of move a metal into a more better situation. Another sort of way is what's known as cathodic protection. And with cathodic protection, for example, magnesium can be connected by a wire to a pipeline or tank. So if you take like a tank or something like that and you bury it in the ground, clearly there's a lot of moisture down there and stuff. And to sort of prevent the oxidation of the tank, which is essentially probably what you're interested in since you buried it, you could use something like magnesium, which is a better reducing agent than iron. And remember, a reducing agent is something that gets oxidized. And if magnesium is a better reducing agent than iron, once again here, all the oxidation is going to occur basically at the magnesium, is going to prevent the sort of tank that you buried there from having any significant amount of oxidation or corrosion occurring to it. And obviously, it will allow your tank to be in business for a lot longer than, you have to go dig it up every other month because obviously it's corroding away. Titanium is sometimes used in ship hulls. Again, same idea there. The oxidation occurs here. So as you can see here, the magnesium, again, sort of acting as a artificial or sacrificial sort of electrode. All the oxidation occurring over here. Again, not any significant amount of corrosion happening to your iron tank that you probably buried and are interested in. Any questions on corrosion? So you know what corrosion is, maybe a couple ways to prevent corrosion. Seems good. Yeah. All right, the last thing we're going to talk about in this chapter is actually electrolysis. And electrolysis is actually the process where we apply electrical energy to make a non-spontaneous process basically occur. So these are basically non-spontaneous sort of galvanic cells, if you will. You kind of force it to occur by adding some extra electrical current. And we could make a non-spontaneous process occur, such as if we have sodium chloride, as you can see here, and we put it into an electrolysis cell, it will be able to break it back into sodium and chlorine metal. Basically, it's elements, right? So basically able to break it apart into its elements. We know just taking something like sodium chloride, it will not just spontaneously break apart into sodium metal, right, and chlorine gas. So the important part of this, though, is what is your anode and what is your cathode in this particular situation. And it is opposite of what is going on when you make the ionic compound. So when we make the ionic compound, we take a sodium and we take some chlorine and make a little sodium chloride. I'll do a little balancing like I'm in chemistry class. And in this particular case, the sodium is going from 0 to +1. The chlorine is going from 0 to -1. And in the sort of making of sodium chloride, the sodium is getting oxidized and the chlorine is getting reduced in this case. And that is sort of the process that's occurring when you make that ionic compound. Now, when we do electrolysis, it's really the reverse reaction here. We're kind of taking the sodium chloride and we're going to break it apart into some sodium and some chlorine. Now, going in this direction, which is sort of our electrolysis, our sodium is starting at +1 and ending at 0 in this case. So again, if you went to that sort of number line situation, sodium starting at +1, ending at 0, it is actually the sodium in this case that is getting reduced. So the sodium here is getting reduced. The chlorine is actually getting oxidized. And again, that's because the chlorine here is -1 to 0 in the reverse process. So it's going from -1 to 0, moving in the positive direction. So actually at our anode in our electrolysis cell is actually the chloride being oxidized and our sodium being reduced. So very common mistake people make when they do sort of electrolysis problems is they think about it being made, which is this situation, and they usually will end up getting sort of their anode and their cathode backwards. So again, this process, we're kind of doing the opposite reaction, and you want to make sure that you're kind of going in the right direction in that sense. Another example of electrolysis is the electrolysis of water. You basically can do the electrolysis of water, just take some water, maybe a little acidic water, add a little acid to it, a 9-volt battery and some electrodes, and you can basically break apart water into its elements. And again, this is the opposite process that's occurring than when we make water. Once again, when we sort of make water, we're going hydrogen and oxygen to our water here. And in this situation, what's happening when we form water, again, we're going from 0 to +1. So our hydrogen here is getting oxidized. And going from 0 to -2 here, our oxygen is getting reduced. So we are actually starting with water, though, when we go through the electrolysis of it. And we're going to actually make our hydrogen and oxygen. So again, the opposite things happen here. Our hydrogen is going from +1 to 0. So it's becoming more negative and being reduced. And that's what we see over here in our reduction reaction. We have our H plus going to 0, which is hydrogen gas. And again, the oxygen here is going from -2 to 0. So in this case, becoming more positive and going through oxidation. And that's what we see here, going from -2 to 0 in this particular case. So this is obviously a chemical process that we can break apart water into its elements. And when you do so, you could collect the gas. And as you can see in this picture over here, we have hydrogen gas here in the empty space. And we also have oxygen gas here, also in the empty space. We do see in the picture, as you might expect, we actually collect more hydrogen than oxygen gas. And that's because it's H2O, right? So you got twice as much hydrogen as you do oxygen in this situation. And you typically would collect more hydrogen than oxygen gas in this case. Now, one of the kind of the weird things, if you will, when you come across sort of electrolysis problems, especially electrolysis problems involving water, is a lot of times the questions themselves really won't mention water as like, hey, you're doing the electrolysis of water. But oftentimes what they will mention is something like that. Like, hey, you're doing an electrolysis cell with a dilute solution of like sulfuric acid or some type of acid solution. So typically speaking, if you see an electrolysis sort of problem, it doesn't really mention water, but it mentions something about some dilute acid. It's probably the electrolysis of water. And if you need to use the half reactions, then these would be obviously the half reactions that you would want to use in this situation. Any questions on that there? Now, when we do electrolysis problems, there's sort of a basic format in terms of these type of questions. And very often you will be given, for example, the current of your electrolysis cell. So they'll tell you how long you let that cell run for. So they'll oftentimes give you the current in amperage. And an amp is a coulomb per second. And that comes from this relationship right here. And again, if you just divide the seconds to the other side, that gives you that an amperage is equal to a coulomb per second. They oftentimes, like I said, will give you kind of the time you ran the cell for. I would say that you need to probably convert the time into seconds so that everything cancels out correctly. So a lot of times they will not give you the time in seconds. They'll give it to you in like hours, maybe minutes or something like that. But converting it to seconds will allow everything to cancel out correctly. Now, what would you do with those two numbers? Basically, you would take the seconds you ran the cell for and you would times it by the amperage, and the seconds would cancel, and that would leave you basically a coulomb of charge. And it's at this point that we use Faraday's constant that we've been using before, that F value. And Faraday's constant is there's 96,500 coulombs per mole of electron. So you would then use Faraday's constant to go from coulombs to moles of electrons. And by doing sort of this calculation, you will end up with moles of electrons. And at this point, it does sort of depend on the problem that you're doing as to what your next move might be. One of the moves you probably will do at this point is you would use the balanced half reactions, and you would use those balanced half reactions to go from moles of electrons to moles of whatever you're interested in, be it chlorine, maybe sodium, anything that you may be interested in, hydrogen gas, oxygen gas. At that point, you'll have moles of whatever you're interested in. Then you usually have two options. Sometimes they want to know, how many grams would you produce? So in that situation, you could go from moles to grams. Hopefully you remember, right? That's the molar mass, right, from the periodic table to do that. Another very common ending, once you sort of get the moles of everything, is something like hydrogen gas, oxygen gas, chlorine gas, right? These are all gases, and a lot of times when we think about gases, we're not necessarily always interested in maybe how many grams of the gas we would produce. but we're interested a lot of times in like the volume of gas that you might produce in this particular cell. So that's going to be a throwback to old school here, a little PV equals nRT action. And you may have to use the ideal gas law here in some of these problems to solve for volume. A reminder that when you do use the ideal gas law, the pressure does need to be in atmospheres, the volume should be in liters, N is moles, so that should be moles, and T is the temperature, that should be in Kelvin, where R is your gas constant, 0.08206 liters, atmosphere, Kelvin, mole. Or if you learned 0.0821, you can use that number too, whichever number you like there. So that is also a very common sort of ending to an electrolysis problem. Once you kind of get the moles from the half reaction, they will also give you something like pressure and temperature sort of information, and then you could go into the gas law there. Any questions on any of that there? All right, let's take a look at one here. So why don't you try this one here? How much calcium, so we'll go with how many grams of calcium would be produced in an electrolysis cell of calcium chloride if the current is 0.452 amperage and is run for 1.5 hours. So why don't you take a few moments, see what you come up with. Calcium 4008. Okay, so let's take a look. So in this case, we're taking some calcium chloride. We're essentially going to run through electrolysis cell. We're going to basically produce its elements. So remember that we're looking at sort of this situation that's occurring. And that means that really, when we look at it, we have our calcium. Whoops. That's no charge on that. I wrote it badly there. Try that again. There you go. We're actually going this way. And that, there we go. So we're going from calcium to calcium with really no charge here. And it's going from, again, basically +2 to 0. So it's getting reduced, so it's gaining a couple electrons. And in terms of the chlorine, we're going from this to this. And it's going from -1 to 0. And in that case is becoming oxidized. So this is our oxidation, this is our reduction, or this is our cathode in this case, and this is our anode. Any questions on that there? All right, so we do have the amperage given to us. So we do have 0.452 amperage, which is 0.452 coulombs per second. We're going to run it for 1.5 hours. And in an hour, there's 3,600 seconds. So we'll go 1.5 times 3,600. That's going to go, what is that, 5,400 seconds. Again, I'm converting that into seconds so that everything cancels out correctly. So we'll go 5,400 seconds. We'll times it by the amperage we ran the cell for, 0.452 coulombs per second. Seconds are going to cancel, and that's going to get me here. Looks like 2440.8 coulombs. At this point, we're going to use Faraday's constant to go from coulombs to moles of electrons. So those are going to cancel. We'll divide it by 96.5. And that's going to give us 0.025, and we'll call it 29 moles of electrons. Any questions so far? In this particular case, we are interested in the calcium. So that is where our half reaction comes into place. And in this case, again, we can see it is a 2-to-1 relationship. So for every 1 mole of calcium, we get 2 moles of electrons. So we're going to use that as a conversion factor, 0.02529 moles of electrons. And again, 2 moles of electron, 1 mole of calcium. And that's going to get us here divided by 2, 0.0126 moles of calcium. We now can use, since we're looking for grams, the molar mass from the periodic table for calcium, 4008 grams per mole. And that is going to get us here, looks like approximately 0.507 grams of calcium would be produced in this case. So if you ran this cell for about 1.5 hours, you should get out about 0.5 grams of that calcium. Any questions on that there? Now, in this case, we weren't asked about chlorine, but we could have done a similar calculation for chlorine. We again could use the 2 moles to 1 relationship to relate the moles of electrons to chlorine. And at that point, if we were given some maybe pressure, temperature information, you could solve for volume, or you could also solve for grams as well, using the molar mass there of chlorine. Any questions on that one there? All right, then why don't you try this one here, which is really the electrolysis of water. So we're going to run a current of 1.26 amperage is passed through a electrolysis cell containing sulfuric acid for 7.44 hours. Write the half reactions and calculate the volume of each gas at STP. Once again, as I mentioned earlier, you can see in this problem, there is no mention of water, but again, the key word here is some sulfuric acid. So that tells you it is the electrolysis of water that we're doing. So we'll give you the half reactions that we saw on the previous page. 1.26 and 7.44 hours. 1.26 and 7.44 hours. At STP. STP, hopefully you remember, standard temperature and pressure. Temperature is 273 Kelvin. Pressure is 1 atmosphere. All right, so take a few moments here. We're looking for the volume of each gas, basically the volume of oxygen gas and the volume of hydrogen gas. Let's see what you come up with. Okay, so let's take a look here and see. So we'll approach it kind of the same way. We do have how our current there that we're running the cell for. We do have our time. Again, I'm going to convert our time into seconds so everything cancels out correctly. And again, in an hour, there's 3,600 seconds. Going to give us 26,784 seconds. This here again is 1.26 coulombs per second, which is what an amperage is equal to. We'll really use that as a conversion factor here to get to coulombs. 1.26 coulombs per second. Again, they're going to cancel out the seconds. And that will get me 33747.84 coulombs. At this point, this is where we will use Faraday's constant to get to moles of electrons. So I'll just take my number here. And again, we're going to basically divide by Faraday's constant, 96,500 coulombs per mole of electrons. And that's going to cancel. And that will get me my moles of electrons, which looks like it is 0.349 moles of electron. Since I'm interested in really sort of both gases here, I'm going to use both half reactions to basically figure out the moles of hydrogen gas and the moles of oxygen gas. So we'll do our moles of oxygen, and looking at the half reaction for oxygen, 1 mole of oxygen gas will give us 4 moles of electrons. So taking my moles of electrons, using my sort of mole-to-mole relationship from the equation, 4 moles of electrons, give me 1 mole of O2. That's going to get me there, looks like divided by 4, 0.08743 moles of oxygen. I'm going to do the exact same thing here because I do need my moles of hydrogen as well, so might as well just do that while I'm here. Moles of hydrogen, again, going to take the moles of our electrons that we calculated. And going to the next half reaction, couple of options you could do since there is a 4 on the outside. If you distributed that 4 to everybody, you would have 4H plus 4 electrons, gives us basically, let's see there, 4 divided by 2, 2H2. So it basically is a 2 moles of H2 to 4 moles of electrons, which is also the same as a 1 to 2 relationship. So whichever way you want to kind of use that. So I'll just use it like it is in the half reaction. We basically got 4 moles of electrons and 2 moles of H2. Again, the moles of electron are going to cancel, and that will get me 0.3497 times 2 divided by 4. And that's going to give me an error, so try that again. 0.3497 times 2 divided by 4. 0.1749 moles of H2. Any questions up to this point? At this point, it is, we get ideal gas law time if you like. So the PV equals nRT, we're going to solve for V. And at this point, we now have the moles, we have R, we have T, and we do have P. So that is going to allow us to solve for volume. So we do the volume of oxygen. That will be nRT divided by P. Our N for oxygen, 0.08743. Our R, 0.08206. Bless you. Temperature at STP, 273 Kelvin, all divided by 1 atmosphere, which is also STP conditions. So that will yield me here about 1.96 liters of O2. We then basically could do the exact same calculation, except obviously in this case, we're going to substitute in our hydrogen moles. So our moles of hydrogen in this case was 0.1749. Our R, 0.08206. Our 273 Kelvin. And once again here, all divided by 1 atmosphere. Everything cancels out except for liters. And we end up with 0.1749 times 0.08206 times a 273, and that's going to give me a 3.92 liters of H2 in this case. And that is, as we talked about a second ago, basically a 2 to 1 difference, right? We got twice as much volume of hydrogen gas than we do oxygen gas. First off, any questions on that calculation there? Now, because this was at STP, you also do have a workaround, I guess, if you want to think about it that way. If you did not want to use the ideal gas law, and you can only do this because it is at STP, you use that 1 mole of any gas is equal to 22.414 liters. So that is a conversion that you could use, again, because it's at STP. And what you could have done is just took your moles there and use that conversion, and you should get obviously the same answers that you got with the ideal gas law there. First off, any questions on that there? Now, I would say these are very common sort of electrolysis problems. Sort of a variation on these type of problems would be something where maybe they tell you how much you produce, how many grams, or maybe how much volume of a gas you produce in the cell. And maybe you need to back calculate and figure out maybe what the amperage was for the cell or how long you ran the cell. So kind of just working backwards is sometimes a very common sort of electrolysis problems. Any questions on electrolysis here? No? All right, that wraps up chapter 17, they say. Yeah, looks good. All right, I think we will lay it up there.